All right, so you might have seen this table before. It's basically what is called as a reactivity series. Reactivity series. And it essentially predicts the activity of various different elements that are present on the periodic table. Hopefully you can compare here that the representative metals, so group 1 and 2, when I say representative, that means the strong metals. Let's just call it representative metals. Those are most active. Of course, group 1, lithium is the highest. And then the second rung is essentially, most of those are transition metals. Transition metals. The point of reference in this chapter we will see will be hydrogen. So this is the reference standard. Reference standard. And the weakest are the coinage metals or noble metals. Coinage metals or noble metals. This series is basically a rough series. It kind of gives you a qualitative assessment. So it's a qualitative series. Qualitative series. And when I use the word qualitative, that basically means that it's giving me an idea as to which element is stronger and more active as compared to another element towards a single replacement reaction, for instance. So higher is an element in this series, more active it is. That means the activity is in this direction. So one can say that lithium is going to be most active, whereas gold is going to be least active. Least active and most active. And this probably also gives you a flavor as to why when you have lithium batteries, they work, this is in part of course, they work so well. Usually the voltage is like 3 volts as compared to the regular AA batteries, which give you only 1.5. And the reason for that is the dramatic electrode potential that you would see in a little bit when I talk about that. So for now, we are going to focus for the next couple slides. We are going to focus on just the activity series. Reactivity towards what? Reactivity towards oxidation, tendency to go through an oxidation reaction. Oxidation, as you know, is loss of electron. So higher an element is in this series, it will have a tendency to go through oxidation and hence behave as a reducing agent. So let's put things in perspective. Let's see if we can apply this concept to a question. I have essentially iron, which is in copper, that gives you Fe2 plus and copper. We actually saw this equation earlier in the first screencast, I think. And then zinc and copper, if you have them react, then zinc is going to get converted into zinc ions and copper will be reduced to copper. The reason why this is happening is, if you go back to the activity series, you can see that both zinc and iron, those are higher in the series as compared to copper. So they would be able to displace copper from its combined form. What that means is, if you take Fe and you put it in CuSO4, which by the way has a deep blue color, you're going to end up with FeSO4, and copper will be precipitated out. So you will have, like a deep blue, peacock blue type of a color. FeSO4 has a mild green color. And copper is a red, brick red kind of a solid, but sometimes depending on the concentration, it looks very dark, very brown, blackish. So that's a possibility. That's what you would see. But all in all, you would see a dark brownish powder that would get generated in your system. Now, realize when you do the same thing with copper and silver, copper is higher in activity than silver, even though both of those are coinage metals. And so they are not as active, they're also called as noble metals. But even within those, since copper is more reactive than silver, it is going to precipitate silver out of the system. And this is the reaction that you are seeing here. Silver, which is in the presence of in the form of rather silver nitrate, and I put a copper wire, and what happens is that copper goes through oxidation and gives you Cu2 plus 2 electrons, and those electrons are picked up by the silver ions and they deposit as metallic silver on top of that copper wire. That's a possibility, or maybe all of it would be at the bottom. That just depends. Another reaction you're seeing here is also an example of single replacement reaction, where magnesium is reacting with an acid to generate hydrogen gas, so bubbling. And you guys ran this reaction, let's see, experiment 23, where we had zinc and magnesium and copper, and only magnesium and zinc showed the bubbling. If you go back to that lab, you can see your observations. Copper actually did not go through that reaction, and the reason for that is because copper lies lower in the activity series as compared to hydrogen. So the sequence is magnesium is higher than hydrogen, which is higher than copper. So one can say that magnesium would be able to displace hydrogen from its combined form, but copper would not be able to do so. That is not going to happen. So let's see if we can actually use this further on, this idea on a real. The question is, given the following three reactions, determine the activity series for copper, zinc, and iron. So you're given that iron is able to displace copper. So hopefully you can infer from here that iron is higher in activity than copper. Zinc is also able to displace copper from its combined solution form. That means zinc is higher in activity than copper. But when iron is put in zinc, no reaction takes place. So hopefully you can see here that zinc is going to be higher in activity than iron, not the other way around. And so combining 1, 2, and 3, you can say that zinc is going to be highest, followed by iron, followed by copper. All right, that brings me to voltaic, or what are called as galvanic cells. Galvanic cells. All right. What are these? These are essentially batteries. These are batteries. That means these will generate electricity from a chemical reaction. These will generate electricity from a chemical reaction. Now, you know that electric current is the flow of electric charge. So when electrons start moving, we say electricity is flowing. So electrons flow through the wire, or ions flowing through a solution, both constitute electric current. And since redox reactions involve transfer of electrons from one substance to another, they have the potential to generate electricity. And so if you have a general reaction, and in this case that's exactly what's going on, we have zinc solid, which is reacted with copper aqueous. We saw this reaction a couple seconds ago. Gives you zinc ions aqueous, and copper is going to get deposited as a solid. I just talked about that. Now, realize that in such a situation, if you have basically taken, you know, if you have taken a beaker and you have taken copper sulfate solution within that, and you essentially immersed a zinc plate in that system. What's going to happen is when zinc metal is placed in that solution, the greater tendency of zinc to lose electrons, so zinc is going to lose electrons, Zn2 plus 2 electrons, and that means that zinc is going to go through oxidation. That means copper 2 plus is going to go through reduction, so Cu2 plus is going to go through a reduction. It's going to gain those 2 electrons and give you copper metal. And so electrons are transferred directly from the zinc to copper. Let's take a big picture look at that. So what I'm saying is that you took a beaker, you filled it with some solution of copper sulfate, maybe it's 1 molar, and you immersed a plate, a zinc plate, into that solution. What's going to happen is that zinc, it has a higher tendency, I gave you that activity series, it has a higher tendency to go through oxidation. That means very readily zinc is going to give you Zn2 plus 2 electrons. And where would those electrons go? They would go nowhere, but um, within this solution is where they would be. So one can say that at this interface we are having a reaction, the oxidation reaction that I just discussed. And so copper, which is present as Cu2 plus, is going to accept those electrons and quickly deposit copper metal as a solid. So you would probably envision that you start with a very nice peacock blue color due to the copper sulfate. CuSO4 is blue in color. But realize you're taking away the Cu2 plus from that solution and you're replacing it with zinc. So your overall reaction, if you add these two, oxidation half and the reduction half, to get the redox, if you add the two, you can hopefully see that the 2 electrons are going to cancel off each other and you're going to end up with Zn plus Cu2 plus gives you Zn2 plus Cu. And so you're forming sulfate, of course, is a bystander ion. You can even write this as zinc plus copper sulfate gives you Zn sulfate and copper. You can write that. So zinc sulfate turns out that's white in color. That's colorless, really. So you're going to lose the blue color. The blue color will be discharged over time. Blue color discharged. Discharge means that it'll go away. And instead what's going to happen is it's going to fade out. The blue color is going to fade out, and instead what's going to happen is that copper is now going to be present in the form of solid metal. So you'll see like a very dark red brown type of a precipitate in this liquid. So red brown precipitate formed. Okay, the next thing is, what if there was a method that we would be able to separate out the zinc atoms and the copper ions from each other and force the electron transfer to occur another way? So what that means is that I don't have like this direct contact of zinc being immersed in the in the beaker, but what if I was able to put that separately? That is what would be referred to as a voltaic cell. So let's take a look at a voltaic cell, or a galvanic cell as it's called. So what we are going to do in this setup is have 2 beakers, 2 separate beakers, one containing a zinc solution, so anything like zinc nitrate or zinc sulfate, those would be great choices. NO3 twice, or zinc sulfate, those will be great choices. Zinc chloride, sometimes some people try to use that. The other one is the copper solution, So copper nitrate is just fine. You usually want to keep the corresponding anion the same, just for consistency. And we are going to dip in a zinc electrode in one case. We are going to dip in a copper plate in the other case. And now, since these are two separate sections, essentially we're going to connect a wire through the zinc all the way to the copper, and you can even connect that to a bulb to see if the bulb will glow or not. Alternatively, you can connect it to a galvanometer or a voltmeter to measure the voltage that gets set up in between the two half reactions. So the flowing electrons would constitute an electric current and essentially could be used to do some electrical work. Now, that's what we have. Okay, so as we run this setup, by the way, is what is called as a voltaic cell. And I'm going to go through every single little detail about this, or sometimes also galvanic cell. Galvanic cell. Okay, so the generation of electricity through the redox reaction would be called this. Together they constitute what are called as electrochemical cells. And electrochemical meaning that the chemical energy within the chemical reactions is going to get converted into the energy of electrons, or the electrical energy, which is utilized to do some electrical work. And so you would say that this spontaneously produces the electric current within the system. Another type of cell, which we are going to discuss much later in this chapter, is what is referred to as electrolytic cell. That actually consumes electrical energy to drive a chemical reaction. So it's opposite, and that would mean that that reaction is a non-spontaneous reaction. It doesn't quite occur on its own. Delta G for that case will be a positive value. So like I was saying, we have a solid strip of zinc which is placed in the zinc nitrate solution, and this is one half cell, and we have a solid strip of copper which is placed in the copper solution. So these strips are what are called as the electrodes. So we have a zinc electrode and we have a copper electrode, which are nothing but conductive surfaces through which the electrons can either leave or enter the half cells. So this beaker essentially is a half cell, and within the half cell is the electrode, which is the metallic strip. So each metal strip, hopefully you can realize that each metal strip reaches an equilibrium with its ion in solution. Well, what's happening is that zinc is in equilibrium with zinc ions, and two electrons are lost, and the copper is in equilibrium with its setup. But of course, you know that the tendency for zinc to go through this reaction is much higher as far as the oxidation goes as compared to copper. So since the position of the equilibria is not the same for both of these metals, for the case of zinc the reaction is way too forward. On the other hand, not so much in the case of copper, and that has got to do with the tendency of zinc to ionize and to go through the process of oxidation. So we will say that the zinc half reaction is going to be further to the right, and as a result of that, you can perhaps envision that the zinc electrode becomes negatively charged as compared to when you compare it in relation to the copper electrode, because of course there is generation of the electrons in the system due to the loss of the electrons. So you would say in that sense, zinc is a negative electrode, copper is the positive electrode. Now, if the two have cells, like I was saying, if they're connected by the wire which is running from zinc and there's a light bulb, you can either have a light bulb or you can have a galvanometer or you can have a voltmeter, either of the three. If you do that, electrons will spontaneously flow from the zinc electrode over towards the copper, and we say that that happens because the zinc electrode, which is more negatively charged, and therefore it's going to start repelling those electrons. So realize this is the electrode which is where the equilibrium at the interface with the zinc solution occurred. So the two electrons that have been lost are going to be pushed through the wire, and as the electrons flow away from the zinc electrode, the zinc ion equilibrium is going to shift further to the right and the oxidation is going to take place. Now as the electrons make it on the opposite end, what's going to happen is that the copper electrode, that is where more and more copper ions from the solution are going to gain those two electrons and actually deposit copper on the plate, and so a reduction reaction is going to take place at the copper end. The oxidation reaction is going to take place at the zinc electrode at that end, and as the flowing electrons constitute electric current, that is going to light up the bulb, or you are going to see a deflection in the galvanometer, or you're going to get a reading for the voltmeter, as the case may be. So realize that the electrode at which oxidation takes place, which is the left side by convention, is also called as the anode. On the other hand, the electrode at which reduction takes place is also called as the cathode. So two words, anode and cathode. You can perhaps remember an ox, 8, a red cat. And anode is where oxidation is, reduction is at cathode. If you can remember that, you should be set for with that mnemonic. Okay, so again, key things to remember: an anode is the negative electrode, which is where the oxidation takes place. Cathode is the positive electrode, which is where the reduction is going to occur. Now, since electrons are moving and rate of electrons flowing through a wire is analogous to current, and current is measured in amperes, by the way. So amperes is nothing but coulombs per second. Let's write that somewhere. Amperes, amps is nothing but coulomb per second. And so one might question that why is it that these electrons are actually moving? And so the driving force for this electrical current, consider that to be similar to the driving force for example, water to go down the hill. You say that a water current is driven by the difference in the gravitational potential energy. So that is the reason why a stream flows down the hill, and from a region of higher potential energy to a region of lower potential energy. So electric current in a similar manner is also driven by the difference in potential energies, and this difference is what is also referred to as the potential difference. And that is what is measured in volts, which is nothing but joules per coulomb. So usually you would see that if there is a large potential difference that corresponds to a large difference in the charges between the two electrodes, there will be a stronger tendency for the electron flow to take place. On the other hand, if the difference is not much, then the tendency would be relatively slower, relatively weaker. But this potential energy, it has a specific name. It is also referred to as the electromotive force, or the EMF. And we are going to spend some time in discussing in, what EMF is and how we calculate it and all that good stuff. But realize that for any combination of cell, and in this case we had the zinc copper combination, but irrespective of what the two electrodes are comprised of, their tendency to go through the oxidation and the reduction cycles is what is going to drive the electromotive force, and hence how well the reaction is going to take place. Now, realize that as electrons flow out of the anode, so as they are moving out, moving away into the wire, basically you're going to build up the zinc ions in the solution. So there's going to be a positive charge built up in your system. Likewise, as you're going to use up those electrons and you're going to use up the Cu2 plus, there's going to be the negative charge, the nitrate, which is going to stay behind in your beaker. And so you can hopefully see that the left part is going to have a very strong positive pull, and then the right part is going to be very negatively charged. Now, and if this kind of a situation, if the movement of electrons from anode to cathode were the only flow of charge, then the buildup of this opposite charge is going to occur very quickly, and this is going to essentially stop the electron flow almost immediately, because the difference, the potential difference that is generated is going to become infinite, or very big very quickly. And so the cell needs a pathway by which a counter ion can flow between the half cells without the solution of the half cells mixing up. For this reason, we use what is called as the salt bridge. A salt bridge is nothing but sort of like a U-tube. It's of the shape of a U. So it's a U-tube, not the YouTube, but the U-tube. It is basically nothing but a glass tube, which is generated essentially. It contains a neutral solution such as KCl or sodium chloride, something which doesn't quite participate, which is not zinc and which is not copper. What we do, obviously, you probably are wondering, well, she put it inverted. How did she put it inverted? And how is the solution still within that setup? And the reason for that is because it is saturated, A, and B, what we do is we mix it with agar-agar. Agar-agar. Those of you who have run some gels in biology would have used this. One is a PAGE, polyacrylamide, which is also a polymer, and agar-agar is another one. Essentially, when it's hot, it's like a liquid, and when it cools down, it solidifies. So it's like jelly. You can consider that like the jello. And what we do is we prepare a saturated solution, we mix it with agar-agar, and we fill the tube with this solution. And now when it cools down, it essentially contains this gelatinous material which doesn't fall off, and it behaves as a salt bridge, which contains a strong electrolyte like KCl or KNO3, which basically connects the two half cells. And so since there's the electrolyte which is suspended in the gel, you're able to sort of prevent the generation of too much of positive charge on the left side, too much of negative charge on the right side. So what happens is that the negative charges, if you used Cl, so for instance, Cl negative is going to come in from the U-tube, and it's going to neutralize the positive charge. Likewise, the potassium is going to migrate into your beaker on the right hand side, and it's going to nullify the negative charge that you have built up at the cathode. And so in other words, it completes the circuit, allowing the electrical current to flow.